Chapter 1, Section 10. In this section, we will look at periodic functions. Our primary focus will be on the sine and cosine functions. We'll look at the amplitude and period of these functions and apply some of the graph shifting techniques you read about in Chapter 1, Section 8. So what is a periodic function? A function is called periodic if its values repeat at regular intervals. So what's going to happen is we're going to notice a pattern that repeats at certain specific regular intervals. Some examples that come up naturally of periodic functions are seasons, phases of the moon, a pendulum on a grandfather clock, your position riding a Ferris wheel when the speed is constant, and the rhythm of your heart. What are some of the measurements of periodicity that we want to look at? The first one is amplitude. The amplitude is half the difference between the maximum and minimum values of your function. So if you take the maximum value and you subtract off the minimum value and divide by 2, that'll give you your amplitude. It's also the measurement of your horizontal baseline to either extreme, the maximum or the minimum. We'll look at graphs of these and how we calculate these directly. We also want to know what the period of each of these functions is. The period is the time it takes for the function to execute one complete cycle, so the time it takes before it begins repeating what we've already seen. Some examples of periodic graphs appear below. Let's start with the one on the left. So here, you'll see that we have some V's and upside down V's or triangles here, and it's repeating because it's the same graph over and over again, and so we can look at the amplitude and period of this graph by looking at each of these little hash marks as one unit. So let's start with the amplitude. We can see that the highest point is approximately 1.5 and the lowest point is negative 1.5. So to get the amplitude, we would take the highest point, 1.5, subtract off the lowest point, minus negative 1.5, which would give us 3, and divide by 2, which gives us a final amplitude of 1.5. Again, it's also the distance from the horizontal line that bisects our graph to either the highest or lowest point. Now for the period, we need to see when it begins to repeat. So if we start here at the 0 mark and keep continuing until it starts to repeat, we make it all the way to this point right here. So if we count how many hash marks we have, we're going to have 1, 2, 3, 4. So it takes 4 values before we start to repeat our graph. So that's our period. If you look at the graph on the right, I've inserted this horizontal line here to help us calculate the period, but let's start with the amplitude. Notice here that the highest point happens at a unit of 1, and the lowest point happens at a unit of negative 1. So if we do 1 minus negative 1, that gives us 2, and if we divide that in half, that gives us an amplitude of 1. For the period, if we want to see how often we repeat, we start looking at our graph to see approximately when we start repeating our graph. That's what this line represents. I drew a horizontal line to see where we would start repeating. It's approximately at the 0 mark, so it goes from negative 6 to 0, so the period is 6. Okay, we're going to start repeating every 6 units. We expect the graph to repeat. Here are some more graphs just to show you that periodic graphs don't have to be smooth and nice all the time. This is what we're going to typically see up in the left-hand top corner. We're going to see what's called a sinusoidal graph, which we'll start looking at soon. But we have other ways of looking at periodic graphs. Down here on the bottom, we have a nice pyramid-shaped graph. Up here on the top, we have something that kind of looks like Batman. We'll call it the Batman graph. Down on the bottom, we have these jagged ridges. But what is the same about all of them is they repeat the same pattern over and over again, which is what makes them periodic. So we're going to focus our studies on trigonometric functions. So the two that we're going to look at primarily are the sine function and the cosine function, which you learned about when you took trigonometry. So here, we'll start with y equals sine of t. The sine graph is a nice wave that's nice and smooth. It starts, if you look at 0, comes up, it peaks at 1, comes all the way down to negative 1, and then gets to 2 pi. The graph stops at 2 pi because that's where it begins to repeat. So the sine graph okay, is going to have an amplitude of 1 because the maximum value is 1, the minimum value is -1. 1 minus -1 is 2, divided in half gives us an amplitude of 1. The period, again, is going to be 2 pi. As you can see in this graph, that's where it ends, right at 2 pi, because that's where the pattern starts to repeat. The cosine graph looks very similar and also has an amplitude of 1. It has a maximum of 1, a minimum of -1, so we know the amplitude is 1. Again, the period is 2 pi. If we start at 0 and we keep going over, at 2 pi we end up where we started and we repeat the graph. So I want you to notice that in sine and cosine, that the cosine function is the same as the sine function shifted pi over 2 units to the left. So that's why they look so similar. It's the same graph, it's just shifted. So what happens when we change things up, when we throw in a multiplier outside and inside? How does that affect our graph? Because that's going to affect both our amplitude and our period when we talk about multiplication. So if we have the graph y equals 6 sine 2t, let's look at the amplitude. What does that do for the amplitude? So here I want you to notice that our new maximum is 6 and our new minimum is -6. So if we do 6 minus -6, that's 12 divided by 2 is 6. So multiplying sine or cosine by a number is going to change the amplitude to that number. So 1 was our baseline, and now since we're multiplying by 6, we have an amplitude of 6. Now what about that 2t on the inside? Normally we just have t. So what does the 2 do? Well, I want you to notice where our sine graph starts. We come up, then we go down, and we loop back around, and when we get to the starting point, we're just a little over 3. As it turns out, we are right at pi. So what happens is, instead of having a period of 2 pi, when we multiply by 2, it divides the period in half. So now we only have a period of pi. I encourage you, when dealing with these types of functions, to graph them to see what's happening and if it matches what you expect to happen. What about if we add something on the outside and something on the inside? So you read about this in Chapter 1, Section 8 in graph shifting. The same thing's going to happen if you're dealing with trigonometric functions. Here, if we add a 4, it's going to shift the entire graph up 4 units. So before, our sine graph had a maximum of 1 and a minimum of -1. Well, by shifting it up 4 units, that means we add 4 to both the max and the min. So now my maximum's 5 and my minimum's is going to be +3. Excuse me. So here, what does that do to the amplitude? Well, our maximum is 5, our minimum is 3. 5 minus 3 is 2, divided by 2 is 1. So if we shift the graph up or down, it doesn't affect the amplitude. It still has an amplitude of 1. Now, on the inside, we have a pi over 2. We can see that our sine graph isn't started where it normally is, because when we add something on the inside of a function, it shifts the graph to the left. This is the counterintuitive one. If you subtract something, it shifts it to the right. So here, we've shifted our sine graph pi over 2 units to the left. So if you add something on the outside or the inside, it's going to shift it, okay, to correspond to that. But I want you to notice that for the period, again, if you start at 0 or you pick any point just to measure, okay, when we get to the next point where it repeats, here we're a little above 6. So the period is still 2 pi. By adding things, it does not affect the amplitude in the period. Only multiplying things towards your sine or cosine will affect the amplitude and the period. So we can write these as general equations. We have y equals a times sine bt plus c, and y equals a times cosine bt plus c. These functions are periodic, and they have the following properties from the general equation. The amplitude of this particular function is going to be the absolute value of a. The period of this function is going to be 2 pi divided by the absolute value of b. That's how often this equation is going to repeat. The vertical shift is how much you are going to raise or lower the graph. So if you add c, it's going to shift the graph up. If you subtract c, it's going to shift the graph down. So now that we know these, we can find a possible formula for the following graph using what we just learned. So if we start with a graph, how do we find the formula? Well, there's 3 big steps that we want to follow. First, we want to decide if the function more closely resembles a sine or a cosine function. Here, I believe this looks more like a sine because it starts at 0 instead of at 1 or something above 0 like the cosine would. So I'm going to stick with sine, although there's multiple answers to this question. Second, determine if the function has been shifted up and down, left or right. So does it stray from the normal horizontal 0? Here it doesn't appear to. It starts and it goes through the zeros like we expect it to. Lastly, we need to determine the amplitude and the period and phase using the graph. So here we start with the amplitude. Okay, so again, what we're going to do is we're going to take the difference of the max and the min and divide by 2. So our maximum value here is 3. We'll subtract off -3, our minimum, and divide by 2. 3 minus -3 is 6, divided by 2 is 3. So our amplitude A is going to be 3. What about the period? So here, our period is 12 pi. That's how long it takes to complete one cycle of the sine graph. So using that, we can solve for B for our general equation. The period is 12 pi, and by using the fact that the period equals 2 pi over the absolute value of B, we can solve for B. So if 12 pi equals 2 pi divided by B, we can multiply the B up to the left and divide the other side by 12 pi, and that will solve to tell us that B equals 1/6. Once we have A and B, we can plug it into our general formula, which is going to tell us that y equals 3 sine of t over 6. Again, 3 is the amplitude, which gets multiplied in front, and b multiplies t. So the 1/6 multiplies the t to give us t over 6. We don't have any shifting, okay, so since we didn't go up or down, we don't have a plus c, and we didn't have any phase shifting, which is the inside, left or right, so we don't have anything added or subtracted inside. So our general equation becomes y equals 3 sine of t over 6. So as you can see, some of the things that we've already learned are applying to this, but we also have some new ideas. So now when we talk about trigonometric and periodic functions, we can talk about the amplitude and the period, and we'll all be on the same page about what that means in terms of the function and the graph.